It hasn't been noticed that Newton's second law, F equals ma, is in fact an expression of Newton's third law. Thus, if we have a free body at rest acted upon by another body, this other body exerts a force F which invokes a counterforce F star equal in magnitude but opposite in direction to the acting force F. Then the net force will be F plus F star, which is equal to ma minus ma, equal to 0. Therefore, if the force described by Newton's second law is the only force acting on the resting free body, then there will be no net force and the body will not move. There will be no motion. If we now call Newton's second law and Newton's third law laws of motion, then this will be in contradiction with Newton's first law, which requires that there should be a non-zero net force in order for the body to change its state of rest or of uniform rectilinear motion. In order for one to get further convinced that Newton's second law is in fact a law of rest, despite the fact that it is usually referred to as a law of motion, one may observe the most general equations of motion in mechanics, Hamilton's equations. Hamilton's equations are connected with Newton's second law. Newton's second law can be derived from Hamilton's equations. Thus we have partial dH dp sub I, where h is the total energy of the mechanical system and p sub I are the generalized momenta, and this is equal to dq sub I dt, where q sub I are the generalized coordinates. On the other hand, we have partial dH dq sub I equals minus dp sub I dt. Now, if conservation of energy is obeyed, is the usual acceptance in mechanics, then we'll have H equals T plus U, where T is the kinetic energy of the system and U is the potential energy of the system, which is, if conservation of energy is obeyed, this must be the constant. But if H, the total energy of the system, is a constant, then these equations are equal to 0. But if that is true, then the generalized coordinate and the generalized momenta are constants. which means that the system is at rest. The system is not in motion. This means that Hamilton's equations are equations of rest, not equations of motion. The incorrect perception that Hamilton's equations are equations of motion rather than equations of rest poses a major problem in classical mechanics and classical physics, leading it further into the abyss of the irrational, away from reality. Suffices it to say that quantum mechanical operators are constructed based on Hamilton's equations. In this way, the problems of classical physics are perpetrated in quantum mechanics, in addition to other problems quantum mechanics has, which will be discussed in other videos. It may be added that the incorrect understanding of motion is the main reason for the crisis of the 20th century physics. Once these problems are realized, one may not help but wonder as to what must be done for this state of crisis to be amended. There is nothing more categorical that may bring clarity regarding motion than the absolute truths of physics. Absolute truths of physics are, for instance, its definitions. Say the definition of velocity, v, equals dx dt. Or the definition of acceleration, a equals dv dt. From these two definitions, we can express dt in two ways. From the definition of velocity, dt equals dx over v. And from the definition of acceleration, dt equals dv over a. Now these two expressions being equal allow us to write dx over v equals dv over a, or a dx equals v dv, which may also be written as a dx equals 1/2 dv squared. Now we can integrate both sides of this equality. Integral from 0 to x, factoring out the constant acceleration a. And on the right side we have integral from 0 to v, factoring out 1/2, from where we get ax evaluated from 0 to x equals 1/2 v squared evaluated from 0 to v. Finally, we have v squared equals 2 times ax. This equality, this parabola, has come about from absolute truths of physics. Therefore, the connection between the velocity v, acceleration a, and the position x is set in stone. It is an absolute truth. And we can plot it and see what conclusions we can get from it. Before drawing the graph of the parabola, we must take notice of the crucial fact that after a force is applied on a free body at rest, the free body is set in motion, traveling across a real non-zero distance, exhibiting inevitably a non-zero displacement delta x. This emphasis is necessary because classical mechanics usually talks about virtual displacement, which even a simple experiment shows has no roots in reality. Even a most simple experiment will show that a free body at rest, acted upon by another body, will be set in motion after the impact, exhibiting a non-zero displacement delta x. In addition to the fact that after the impact the body exhibits a non-zero displacement, the minute one sees that the free body is driven from rest and is set in motion after the impact, one must realize that motion is not just a compilation of states of rest as physics understands it nowadays, but there is more to it. Motion inevitably involves a change in one important additional quantity, namely energy. Motion under the action of a constant force inevitably involves change in kinetic energy. We saw that if we agree to call Newton's second law a law of motion, it will be in contradiction to Newton's first law, because the force described by Newton's second law inevitably invokes a counterforce, an inertial force, which compensates it. While Newton's first law allows for a change of state of a body, for instance, a body that has been initially at rest, to be set in motion, only when it is acted upon by an uncompensated force. The contradiction in Newton's laws, when labeling them laws of motion, stems from ignoring absolute truths of physics regarding motion, easily demonstrable experimentally. To illustrate this, we'll go back to the absolute equality we've already derived based on absolute truths of physics. V squared equals 2 times ax. This was derived based on the definitions of velocity and acceleration. Here is the graph of this parabola. X, V. And if we now are to honor that the body is in motion, we cannot speak of a fixed position of that body in space corresponding to a fixed velocity. In order to honor that the free body acted upon by a constant force is in motion, we must always consider the non-zero change of position in space, delta x, of that moving body, as well as the change of velocity, the non-zero change of velocity of that moving body. It's true that at a given time t, the body in motion has a given x corresponding to a given v. But this only reflects the effect of force in time and neglects the effect of force in space along the displacement, where the body changes its velocity, respectively its kinetic energy. Therefore, if we want to address also this aspect of force, the spatial, the effect of force in space along the displacement, we must observe intervals, changes, delta x and delta v. Observing the effect of force only in time, as is done in contemporary physics, is only a limited way of understanding force. It isn't incorrect, but it limits the essence of force, neglecting the effect in space of force deprives force from its proper description of motion. Once it's understood that the motion of a free body under the action of a constant force necessarily involves non-zero displacement and a corresponding non-zero change of velocity, we are ready for some dramatic conclusions. Firstly, it shows that D'Alembert's principle is invalid for a free body in motion under the action of a constant force. Also, it indicates that the determination of the position and momentum of a free body moving under the action of a constant force is always connected with uncertainty. The equation expressing D'Alembert's principle is obtained from Newton's second law, F equals ma, by reordering it and then multiplying both sides of this equality by the displacement, which usually is considered to be a virtual displacement. Lowercase delta x. However, we saw that the motion of a free body under the action of a constant force causes the body to travel along a real non-zero displacement delta x. So in order to be physically consistent, we must multiply this expression in the parentheses by delta x, which again is equal to 0. However, it is immediately seen that the left side of the equation expresses work, A. And it is obviously impossible for a body to be transported across a non-zero displacement delta x by spending zero work. This is a non-physical expression, and we have to amend it. Now the amendment comes about easily once we remember that the non-zero displacement delta x is inherently connected with the change of velocity, this delta v. So delta x and delta v are like Siamese twins. They are inseparable. And here of course, we can write, instead of delta x, we can write x, because we start from 0. The displacement starts from 0. X. And we have x, and we have delta x. And we have delta x is equal to x minus 0, which is x. So we may write x here instead of delta x. And we can write here delta v. We can write v instead of delta v. So the amended expression will be f minus ma times x equal to mv squared over 2. This is the kinetic energy which the body acquires at the end of the displacement, which the body has at the end of the displacement. Now this form, this amended form of D'Alembert's principle, has far-reaching consequences, and we saw in another video how the relationship between energy and mass comes about from this amended form of D'Alembert's principle. Also, as was already said, the non-zero character of delta x and delta v when a free body is in motion under the action of a constant force inherently expresses the uncertainty with which the position and the momentum of a moving body is determined. So if we write here instead of delta v, if we this delta v is for mass unity, but if we have any mass, then we can have delta mv. And of course the character of this parabola will change corresponding to another m, to a different mass. And of course this is momentum, and more exactly the change of momentum. Now the fact that change of momentum is different from 0 and delta x is also 0 shows that their product dp times dx is never zero when a free body is in motion under the action of a constant force. But this is an expression of an uncertainty principle. Uncertainty principle, which, as we see here, is an attribute of classical physics. It comes about due to the absolute truths of classical physics. So this delta p delta x is equal to, say, some delta lowercase w, and this is different from zero. This is greater than zero. Now we see that uncertainty principle exists in classical physics, unlike the current impression that uncertainty principle is an attribute only of quantum mechanics, and it's one of the characteristics of quantum mechanics. And when we go from the micro world of quantum mechanics into the macro world of classical physics, uncertainty principle is no more. We see here that this is not the case. Further, we'll see some peculiarities connected with this classical uncertainty principle. The dimensions of the quantity called action, which is a measure of motion, are as follows: delta p times delta x, which is action, is m delta v times delta x, this is delta p, which we may write as m delta x over delta t times delta x. And as is seen, this is kilogram meter squared times second to the minus first. These are the dimensions of action. On the other hand, we know that joule is kilogram meter squared second to the minus second, and therefore, if we want to express it in joules, the dimensions of action are joule second. Kilogram meter squared second to the first, or joule second, are also dimensions of the so-called Planck constant, which is considered to be the threshold, the cutoff point between classical mechanics and quantum mechanics. It is considered that the minute one sees Planck's constant in a formula, then this is a sign that we're in the realm of quantum mechanics. Planck constant is determined experimentally in the work of Lummer and Pringsheim in 1899. However, as we saw, action is in fact an inevitable characteristic of motion in classical mechanics. Obviously, there should be a lower bound of the classical action value, dependent on the dimensions of the smallest particles of matter, such as radius of electron, mass of electron, velocity of electron. This will allow to calculate the elementary quantum of action in classical physics. This value, the elementary quantum of action in classical physics, can be compared with the value of the elementary action in quantum mechanics, which is the so-called Planck constant, determined experimentally, as we said already, by Lummer and Pringsheim. This comparison will help to understand how accurately these determinations, experimental determinations of these quantities was done. Now we will proceed with our discussion based on absolute truths. The necessity to follow such an approach follows from the fact that basics, fundamentals of physics, are thought to be so well established that any attempt at correcting them will inevitably meet with insurmountable opposition. However, any rational person would agree that absolute truths are the cornerstone of any argument. And if it is found that fundamentals, that the basics of physics are at odds with absolute truths, such a finding must not be ignored if one really thinks that rationality is the real foundation of science. We will observe the graph of the absolute equality v squared equals 2 times ax for a constant acceleration a equal to 1/2 meters per square second, which gives v equals square root of x. Now this equality, this parabola, is written for mass unity. So for any mass m, we have momentum p equals mv, which is equal to m square root of x. Now, when looking at the graph of this absolute equality, one may think superficially that all there is to it is that to every given position in space, there is a given value of momentum corresponding. And this way of looking at the graph is not incorrect, but this is a limited way of looking at the properties of this function. This limited way of understanding the function leads to the incorrect impression that all there is to motion is that motion is a compilation of states of rest, of these states of these x's to which corresponding momenta are attached, are mapped. This, as I said, is not incorrect, but this is a limited way of looking at motion. And this limited way of looking at motion is the cause for all problems that contemporary physics has. The dead end that it is finding itself into, leading it to creating areas which don't have roots in reality, which are non-physical, such as quantum mechanics. And the fact that quantum mechanics is not understood physically, but is only used today as recipes for calculating certain practical problems, has its roots in misunderstanding, is in ignoring, in limiting the understanding of the essence of motion. Rooted in this problem here. Now, properties of function in mathematics, of course, are not limited to only mapping of x onto p, of observing only this connection between p. But mathematics also considers that at every point of this curve, there's a slope. And this slope is non-zero, which is very important for us for this discussion. So, even according to mathematics, there is more to the function p equals m square root of x. At every point of the curve, there is a slope. For instance, at point A, the slope is dx, dp, dx, which is equal, say, to 2. Just to make things simple. Now, at point B, there's also a slope, dp dx, of value, say, 1. So, if we're to express dx, here at point B, dx will be equal to dp, but at point A, dx will be dp over 2. Now this fact leads us to a major conclusion. We can express from these values here, we can express the values of the action at these different points of the curve, these different areas, and what we get is that at point A, the action dw is equal to dx, which is dp over 2, times dp, which is dp squared over 2. While at point B, we get dw, this is the action, equals dx, dx is dp. At point B, we have dp times dp, which is dp squared. What we see here is that action is not constant. Action, the value of action, changes as the motion progresses. The longer the constant force F acts upon the free body, the greater the value of the action becomes. But this is contrary to the basic principle which is accepted today in physics. the principle of least action. According to the principle of least action, when the generalized coordinates of a system change during its motion, action must remain constant. But as we see here, it isn't so. Action changes with x. Now, it may be more instructive to observe deltas, delta x and delta p, instead of dx and dp. As you see here, as the motion progresses, as the position of the body increases under the action of this constant force acting on the free body, the value of the action becomes greater than its value somewhere around the beginning of motion. Now this shows that if we keep the effect in space, which is ignored in contemporary physics, but there is an effect in space of the acting force. So if we keep this effect delta p constant, we see that in order for this spatial effect of the force to be constant, as the motion progresses, it needs a longer path, it needs a longer displacement to achieve the same effect in space. We can see action for the same area here, for the same region, that when the mass is lower, the action in the same region is greater. This means that these values of action for a lower mass have been observed earlier in the motion. The smaller the body, the earlier it will experience this measure of motion, action. Also, it is interesting, and it resembles conclusions in quantum mechanics, that the longer the constant force acts on the free body, the more we get into the motion, the higher the x, the less precise is the determination of the position of the body in space. You see, delta x of this body at greater x is larger than delta x at lower x's, at the beginning of the motion, at the beginning of the application of the constant force onto the body. Similar effect, of course, is observed when we keep the displacement constant, the change of position constant, with the increase of x, of the position of the body in space. As we see, as the motion progresses at higher x's, the measure of motion, action, becomes lower and lower compared to its value at the beginning of the motion, at the beginning of the application of the constant force upon the free body. This means that for a given displacement, delta x, as the motion progresses, with the increase of x, the position of the body in space, the spatial effect delta p gets lower and lower. Also, we can see that for lower masses, such as the trajectory described by curve 1, for this area of x's, of positions, the measure of motion, action, is even lower than a measure of motion, action, for higher, for greater masses. This again means that these values of action have already occurred earlier at the beginning of the motion for lower masses m. In classical physics, the principle of least action, or the principle of stationary action, is considered an inviolable principle, whereby the action doesn't change, remains constant when the generalized coordinates of the mechanical systems change. It is expressed in this way: the action S, which is equal to the integral of the kinetic potential T minus U, where T is the kinetic energy, U is the potential energy, dt. This is also called Lagrangian, denoted by capital L. And according to classical physics, delta S, this is the variation of action. It's the variation of this integral. And according to classical physics, this variation must be zero. From where S, which is equal to integral from t0 to t1 L dt, must be constant. While, as we already saw, it follows from the absolute truths of physics that action most definitely changes with the change of coordinates, both for a given change of momentum and for a given displacement. As we saw, the absolute truths of physics tell us that if we talk about motion, when there is motion, there must always be a couple delta x, delta p, non-zero couple. And there must always be a non-zero product of this couple, delta x times delta p, must always differ from zero. They, and this, of course, we can denote by delta W. This is the action, this is a classical action. Which is the measure of motion in classical mechanics. And the principle of least action, principle of stationary action, is enforced, is obeyed only when this classical action delta W is approximately 0. In all other cases, when there is motion, delta W must be non-zero. Now, speaking of delta W 0, this is when the body is at rest, and according to the absolute truths of physics, a body can be at rest. Unlike this conclusion based on absolute truths of physics, quantum mechanics never considers rest. There is no rest in quantum mechanics. There's no rest in quantum mechanics because, according to Heisenberg's uncertainty principle, delta x times delta p is always greater or equal to h bar over 2. Now, h bar is the so-called reduced Planck constant, which is equal to h over 2 pi. As seen, if the uncertainty in the position of a body is 0, that is to say, if a body is at rest at a given position, then delta p will be infinity. H bar over 2 delta x, and if this delta x is equal to 0, then delta p will be infinity, which is physically impossible. And vice versa, if delta p is 0, then delta x will be infinity. So, according to quantum mechanics, there is no rest inherently. However, as we saw, the absolute truths of physics require not only that when a body is in motion, delta x times delta p, the action, to be non-zero, but when the body is at rest, that is, when delta x is 0, then this product will be 0, and this product is 0 at rest. There can be rest in classical physics. And one should say, not only in classical physics, but in physics as such, because these definitions of velocity and acceleration are absolute truths of physics, and any conclusion in physics must obey these, must not be in contradiction to these absolute truths. And if there were not to be a contradiction with the absolute truths in physics, then there must be a state of rest or a uniform rectilinear motion, which is akin to rest. At uniform rectilinear motion, the product delta x delta p is also 0. Quantum mechanics never considers rest. There is no rest in quantum mechanics. And this goes contrary to what is expected from these absolute truths that we were citing all the time. This had led physics astray, away from notions based in reality, creating some irrational, fantastic world with no roots in reality. And that is the basis of this. The cause for this is misunderstanding the essence of motion, and especially the special effect of a force acting on a free body. Quantum mechanics, physics, classical physics rather, that's why quantum mechanics appeared, only considers the effect in time of the force. It always neglects the effect in space of that constant force acting on a free body. We can arrive at classical action also from the absolute truth that the transport of a free body across a non-zero distance delta x cannot be done without doing work, as the D'Alembert principle requires. Therefore, we must write work A, which is equal to F real minus MA times delta x. This must be equal to the non-zero value of the kinetic energy, m v squared over 2, and not to 0, according to the principle of D'Alembert. This may also be written as F real minus m delta v over delta t, delta x equals mv squared over 2. Now we can open the parentheses. Delta x equals, and we reorder, of course, m delta v over delta t delta x plus mv squared over 2. Now we can multiply both sides by delta t. Delta x delta t is m delta v over delta t delta x delta t plus mv squared over 2 delta t. These delta t's cancel out. So we get F real delta x delta t equals m delta v delta x is the first term plus mv squared over 2 delta t as the second term. Before continuing, we should recall where this delta v came from. This delta v came from the constant acceleration seen in the linear dependence of velocity v as a function of time. The constant acceleration is the slope of this line. The slope delta v over delta t. This delta v is not the delta v that came up when we were discussing the parabola v squared equals 2 times ax. where we observed the functional dependence of momentum, that is of mass times velocity, as a function of x, as a function of the position of the body. The remark just made was added to make a distinction, to avoid the confusion between the momentum in the first term after the equality on the one hand, and the momentum is a function of the position of the body expressed by the parabola v squared equals 2 times ax, which we discussed earlier, and which expresses the spatial effect of force. This momentum as a function of the position of the body, expressing the spatial effect of the force, is ignored in contemporary physics. And as was already said, it must be considered. As was already emphasized, ignoring the effect of force in space limits the description of motion as a result of the application of force on a free body. Action, as a description of motion, involves both terms on the right side of this equation. Usually, however, we observe it in a limited way, separately. For instance, second term may be observed, may be ignored. Then we get F delta x delta t equals m delta v delta x. Delta x is cancelled out on both sides, and we get F delta t equals m delta v. But this is the usual form of Newton's second law. Indeed, F equals m delta v over delta t, which is F equals ma. This part, the first term, expresses the effect of force in time. Now, if we ignore the first term in the equation, we get F delta x delta t equals mv squared over 2 delta t. Right? Delta t cancels out, and we get F delta x equals mv squared over 2. In other words, F delta x is equal to energy. Now this second part, second term, is the term which expresses the effect of force in space. It is seen now that this compound, this overall action, In fact, the real action, which characterizes the motion of a body under the action of a force, contains both the momentum space action and the energy time. This is energy delta t. Energy time action. The compound quantity action, which characterizes the motion of a free body as a result of the application of a real force. A compound action which consists of momentum position action and energy time action is in fact a combination of the two views existing in physics about the action as a measure of motion. According to one of these views, action is a measure of motion which is a result of the effect in time of the applied force. This view was held by scientists such as Galileo, Newton, Lorentz. The other view, which observes action as a measure of motion, invoked by the effect of force in space, was held by scientists such as Leibniz. Now this combined compound action combines, as was said, these two views. As far as force is concerned, nowadays, when force is considered in physics, it is only the effect of force in time, that is the change of momentum per unit time, that is had in mind. This leads to the impulse F delta t equals m delta v, which has been considered the measure of motion by scientists such as Galileo, Newton, Maxwell, Lorentz. On the other hand, physics inevitably recognizes force times displacement as work. That is, as energy that was spent to do that work. However, the term expressing energy per unit spatial displacement is never part of the equation of force in physics, leaving in this way motion to be considered only as a compilation of states of rest, depriving motion from its qualitative transformations expressed by energy. This energy, which Leibniz has thought to be the measure of motion, this limited way of describing motion in physics nowadays has led it, as was already mentioned, to the dead end of irrational creations and topics which have no basis in reality. Also, it may be important to emphasize, because it is often forgotten, that not all mathematical expressions, not all mathematical equations have physical meaning. For instance, Lorentz transformations, as was discussed in another video, have no roots in reality. They have no place in physics because they have no physical meaning, and any conclusion based on these equations will have no physical sense, makes no physical sense. On the other hand, the equation which was probably the basis of this video, v squared equals 2 times ax, is an equation of unrecognized so far, deep and far-reaching meaning, much greater importance than just a marginal educational discussion that it is used for occasionally.